Hello, and welcome to the beginning of our course on thermodynamics. Here we're going to be talking about something you're already familiar with, which is the ideal gas law. This is our starting point, and we're going to be adding on to this. So we want to make sure everyone's familiar with the ideal gas law and where it comes from and the assumptions behind it, when it's useful and when it's not. So this is one we're going to use on a regular basis throughout this class. So just as a reminder what the ideal gas law is when we're talking about gases, that we have this equation PV equals nRT, where P is the pressure of the gas, V is the volume, N is the number of moles, R is the gas constant, and this can be found in a variety of units, and T is the temperature. And this temperature, unlike the rest of these, which are often, well, moles is in units of moles, but pressure, volume, and R can come in various units, but N is always in moles and T is always in Kelvin. We don't use Celsius in the ideal gas law. So, where did this ideal gas law come from? Maybe you haven't thought about that question, but this law, I'll say law in quotes, comes from a bunch of observations that were made in the 16 to 1800s, so over the course of a couple hundred years. So this relatively simple equation we have is based on quite a bit of experimental work done by various scientists throughout that time. So we'll just look at a couple, look at some of these, not in a lot of detail, but first, Charles Boyle discovered Boyle's law, which is that if you take the pressure and volume of a gas and multiply them together, it's equal to a constant. Or we can rewrite that. Another way of saying this is that if you have a gas at pressure 1 and volume 1 and you change something about it, the pressure times the volume is the same at the other state that it reaches. So that's our first one. Next is Charles's law. And Charles's law states that volume over temperature is equal to a constant. Or again, we can rewrite this one the same way as we did the pressure and volume relationship in Boyle's law by looking at two different volumes and temperatures. For an ideal gas, the ratio of the volume to the temperature is equal. Again, temperature being in Kelvin. All right, this won't work if temperature not in Kelvin. Then we have Gay-Lussac's law. I'm probably butchering that pronunciation. And here we're looking at pressure over temperature, and that is equal to a constant. Or again, P1 over T1 is equal to P2 over T2. And as we're going through these laws, you can see how these all are part of the ideal gas law, right? Where we could rewrite this to say that volume and temperature are inversely proportional to each other, but pressure and volume pressure and volume are inversely proportional. They multiply together and they're equal to a constant. Whereas volume and pressure and temperature, you have to divide them. Okay, and one of the probably most important of these individual laws is Avogadro's law. And you may recognize Avogadro's name from Avogadro's number. And this is related to moles, of course. This helped to establish the idea of atoms and molecules and moles, was this law that was discovered, which is N over V is equal to a constant. Or N1 over V1 is equal to N2 over V2. And if we take all these and combine them, we get the final version of the ideal gas law that we're all familiar with. Oh, it stopped moving. But that PV equals nRT. And that's just a combination of all these laws.